Alright, so good everyone, you're welcome back to the YouTube channel Learn Maths. Today we're going to be looking at partial differentiation, right? Partial differentiation. I believe by now we're all familiar with the regular differentiation whereby you have a function like y equal to 2x squared and you're asked to find just dy dx, right? For this kind of function, you just go straight to differentiating the function y. Right now, this is going to be 4x, right? You see how easy that was. Now, for partial differentiation, we're not going to have a function like this. We're not going to have just a function f of x that is going to be equal to some numbers or terms, right? And a variable x. Now, we're going to be dealing with functions that are actually a function of more than one variable, right? Now, this function here happens to be a function of x, right? And we're going to be seeing functions of variables like x, y, right? Now, this function now depends on two variables, x and y. So if we're asked to differentiate this kind of function, we're going to be applying partial differentiation, right? As we differentiate this function partially with respect to x and then differentiate it partially with respect to y. You may have also functions of x, y, and z, okay? You may have a function of x, y, and z at once, you understand? You differentiate with respect to x, you differentiate with respect to y, and you differentiate with respect to z, right? So we're going to take an example, and I hope you all understand as we proceed. Okay, let's say we have a function f, right, which is a function of x and y, and it's giving us x squared plus xy. Now we're asked to find dy. Okay, we're asked to differentiate it, find the gradient of this function, which you can actually represent as the gradient of the function f, right? Now what do we do? How do we go about this? Remember I said you're going to differentiate it partially with respect to x and then partially with respect to y. So let's see. We're going to have to differentiate this function, right? This whole function x squared plus xy, differentiate it partially. Now that will be with respect to x, right? And then we're also going to differentiate this whole function x squared plus xy, but with respect to y this time around. Okay, first differentiate with respect to x, then with respect to y. So let's proceed with respect to x. Now the gradient of this function is going to be, how do we differentiate this with respect to x? Now this is x, right? This is x squared. If you differentiate x squared with respect to x, you're going to get 2x, right? That's easy to understand, right? Now how about this xy? If you differentiate xy with respect to x, what are you going to get? Now this function, this term xy, has both the variable x and y in it, right? If you want to differentiate this with respect to x, then you're going to assume y is a constant. So let me write this as y x, right? I'm going to assume y is a constant. Now the power of x here happens to be 1, right? You multiply that power with the coefficient of x, which is this constant y, right? That's going to be y. Then you reduce the power of x by 1 and that will become 0. So at the end of the day you have yx raised by 0, which is going to end up leaving you with just y, right? So if you're differentiating a function, a term that has both x and y in it with respect to x, you're going to assume that y is a constant, right? So if we differentiate this xy with respect to x, we're going to be left with just y. You saw how we did that, right? You assume y is a constant, you multiply the power of x with the constant, then you reduce the power of x by 1. So x is going to be gone, leaving us with y, right? So this is the partial differential of this function with respect to x. Let's see what the partial differential of this function with respect to y is going to be. Now this is x squared. How do we differentiate x squared with respect to y? Let's do that in the rough here. Now this is x squared, right? You want to differentiate this with respect to y. Remember now, we are differentiating with respect to y. So we're going to assume that x is a constant, right? X is a constant. Y is going to be the variable here we're differentiating. Now this is just x squared. There is no y there, right? So I can introduce y in this format. This is x squared, the same thing as x squared times 1, right? That's the x squared. Nothing changes. Now I'm going to introduce y as 1. That's y raised by 0. This is still 1, right? Exactly, that's 1. So I've introduced y now in this term, so you understand what we're actually doing here. Now how do I differentiate this with respect to y? Because there was no y here actually. Now I'm going to assume this is a constant because we're differentiating with respect to y. Every other term, be it x, z, or whatever they call it, is going to be a constant, right? Y is going to be the only variable here. So how do I differentiate this now with respect to y? The power of y here happens to be 0, right? You multiply 0 with the coefficient or the constant attached to it, right? Multiply 0 with that, it becomes 0. Then you reduce the power of y by 1, which is not going to matter because we still have 0 in front. So 0 is going to, and it's just going to be 0, right? It's just going to be 0. Or you can just understand it this way. This is x squared, right? This is x squared. And now since it doesn't have y attached to it, this is going to be a constant. And the differential of every constant is 0. Alright? So differentiating x squared with respect to y is going to give us 0. How about we differentiate xy now with respect to y? Xy. Okay, we differentiate xy with respect to x and give us y, right? Now we're going to differentiate xy with respect to y, and it's going to give us x, right? This is why we want to differentiate. So x is going to be the constant. You understand? X is going to be. So if x happens to be the constant, how are we going to go about the differentiation? Now this is why the variable we're differentiating with respect to the power of y here happens to be 1, right? So I'm going to multiply this power of 1 with the coefficient of x, and that's going to be x. Then I reduce this power by 1, that's going to be 0, and y is going to be eliminated the same way x was, right? So differentiating xy with respect to x give us y, and differentiating xy with respect to y give us x, right? So this is going to be x here. Alright, so this is the partial derivative of this function with respect to x, right? We differentiated this function with respect to x, give us this, and then we differentiated the same function with respect to y, give us this, right? So the final answer, that's the gradient of this function, is going to be, this is 2x, and this is x, that's a total of 3x, right? Then this is y. Alright, so that will be the differential of this function with respect to x and y, right? Okay, let's take another example to just, make us understand better, right? I'm going to take this example, this function, f of x and y. Now this is a function of x and y, right? And it is giving us, okay, let's say x squared y plus 2xy squared plus y squared, right? Let's differentiate this partially and get the gradient of this function. Okay, we're going to get the gradient of this function. Now, first things first, we're going to differentiate this whole function with respect to x. Okay, it's becoming long. I may not have to write out everything. Okay, let's just say f of x, y. That's this whole function here, right? I don't have to write out everything there, every term there, the way I did for the first one. Okay, plus the partial differential of partial derivative of this same function, f of x and y, but now with respect to y. Okay, so let's see what we're going to do for the differential of this function with respect to x, right? Let's differentiate this whole function with respect to x. These 3 times 1, 2, 3, we're going to differentiate them with respect to just x, right? Now how do we differentiate this with respect to x? Okay, let's do that on the rough for better understanding. Now that's x squared y, right? I want to differentiate this with respect to x, so I'm going to take y to just be a constant. Since we're differentiating with respect to the variable x, I'm going to take y to be a constant, right? Now the power of x this time around is 2, so I'm going to multiply 2 with the coefficient of x, that is 2y. Do you understand? That's going to be 2y. Then I'm going to reduce the power of x by 1. That's going to become 1, right? So the differential of x squared y with respect to x is 2yx or 2xy, right? So let's put that down here. Going to be 2xy. You understand, right? Okay, now the next step to differentiate with respect to x is going to be this 2xy squared. Okay, we're going to differentiate that with respect to x. Now what's going to be? It's going to be, okay, it's going to be 2y squared. Should we show working? Okay, let's show the working here. We differentiated what? 2xy squared with respect to x, right? With respect to x. So what's it going to be? I'm going to rearrange this as 2y squared x, right? I'm going to rearrange this as this. Then we're differentiating this with respect to x. So every other term, including this y, is going to be a constant, right? The power of x here happens to be 1. So I'm going to multiply 1 with the coefficient of x, respective of how big it is. Okay, multiply this with 1 is going to become 2y squared, right? How about x? What do we do with the x? We reduce the power by 1, it becomes 0. X is eliminated once again, leaving us with 2y squared. So that's how we got 2y squared when differentiating the second term with respect to x. Now let's differentiate the last term with respect to x. You can guess what the answer is, right? 0. It is 0 because there is no x here. There is no x here, right? I can still show you how it is 0 by saying this term here, y squared, right, can be written as y multiplied by 1, which is y squared. Then I introduce x as x raised by 0, since from indices anything raised by 0 is 1, right? Now you have your x in view. You can now differentiate this. If this was confusing, saying the differential of this is 0, if it's confusing, this is how we go about getting the 0, right? You introduce x. Now differentiate this with respect to x. You're going to multiply 0 with the coefficient, it becomes 0. Reduce it by 1, right? You reduce the power of x by 1, it doesn't matter, because whatever you get is going to be multiplying this 0 here to give you 0, right? So the differential of y squared with respect to x is going to be 0, right? The differential of y squared with respect to z is going to be 0, since there is no z here. The differential of y squared with respect to b is going to be 0. Differential of y squared 0, all right? So this is going to be 0. I don't have to include that, right? Let's just take it as the partial differential of this function with respect to x. Now let's find the partial differential of this same function, but now with respect to y. What is it going to be? We're going to differentiate these three terms again, but with respect to y, right? Now let's differentiate this first one with respect to y. What is it going to be? It's going to be x squared, right? Do I have to explain? It's going to be x squared, right? Then differentiate this second term, this other term with respect to y. What is it going to be? It's going to be 4xy. Do I have to explain? Okay, let me just explain, because I don't want to leave anybody behind. Okay, my rough is filled up. I'm going to make use of this space here. Now we differentiated what? 2xy squared with respect to y, right? Now this is going to be the constant. Any letter, any term, any number, any value that is not y is going to be a constant, since we're differentiating with respect to y, right? Now the power of y happens to be 2. We're going to multiply this 2 with this coefficient. That's going to become 4x. Then we reduce the power of y by 1. That's going to be 1. And that's how we got 4xy, right? That's how we got 4xy. We differentiated this. Now let's differentiate the third one, still with respect to y, right? Now this is going to be 2y, right? The differential of y squared with respect to y is 2y. You multiply this by the coefficient, which is 1, gives you 2, right? You reduce the power by 1, gives you 1. So this is going to be the partial derivative. Okay, this is the differential, the total. Since this is partial, that's the total in total, right? So this is going to be the gradient of this function with respect to both x and y. Can we sum up some terms there? Okay, I have 2xy and I have 4xy. That's a total of 6xy, right? I have y squared here. There is no other y squared. So that's just going to be 2y squared. Then I have x squared. And finally, I have, we have 2y. So this is it. This is the gradient, right? Finally, before I end this video, let's try out a function that depends on more than two variables. Let's say x, y, and z. Okay, let's take a function of x, y, and z, right? And let's assume this function is giving us 2x squared z plus 4xy z. Okay, raised power 2. Differentiate this with respect to x, y, and z, right? Now, this is going to be the gradient of this function, as the differential of this function is going to be the partial differential of this function with respect to x plus the partial differential of this same function with respect to y. I don't have to write this is long, right? My ink is going to run out. I'm going to run out ink. So plus the partial differential of this same function, this function, but now with respect to z, right? This function. Let f just stand for the function. You know what the function is, right? A function of x, y, and z. This is what it's giving us. These functions. Alright, so let's differentiate this function with respect to x. Let's differentiate this with respect to x. Now, if you're differentiating this first term with respect to x, every other term attached to it is going to be a constant, right? So I'm going to extend my rough. I am going to extend my rough. Okay, so let's take this as rough as well. Okay, let's differentiate this term here, 2x squared z. Let's differentiate it with respect to x. Now I'm going to rewrite this as 2zx squared, right? Then take 2z as a constant, then differentiate it with respect to x, right? So I'm going to multiply the power of x with the coefficient. That's going to be 4z, then x raised to power, you reduce it by 1 as usual. It becomes 1, right? So we have 4zx, or you can just say 4xz. So arrange them alphabetically. It's going to be 4, okay? X comes before z, right? Okay, that's for this term with respect to x. Now let's look at this term with respect to x, this function here. Let's look at this with respect to x. That's going to be, okay, 4. That's going to be 4yz squared, right? X is going to leave us. If I'm to explain that, this is what it is. 4xyz squared, that's this. Want to differentiate this with respect to x, right? So I'm going to rearrange this as 4yz squared, then x stays here. Since we differentiate with respect to x, this whole term here becomes a constant, right? You multiply the power of x with this, becomes 4yz squared, then reduce it by 1, becomes 0. That's how x left us. Okay, so this is going to be the differential, the partial differential of this function with respect to x. Now, how about the partial differential of this same function with respect to y? For this first term, there is no y there, right? So we can just say the power of y there is actually 0, and the 0 is going to multiply everything to just result in 0, right? Understand it that way. There is no y here. Want to differentiate this with respect to y? There is no y there. It's going to be 0, like it was in previous times, right? So let's just proceed to the next term. We've differentiated this with respect to y, and it gave us 0, right? I don't have to waste my ink on 0. You know it's 0, right? Now let's move on to the next term and differentiate that term with respect to y. All right? Let's differentiate the next term with respect to y. Now there's y there, so you can just assume it's 0. You can just say 0, right? So how do we differentiate 4xy z squared with respect to y? Z squared with respect to y. I take this as a constant. The power of y there is 1. 1 multiplies this, it becomes 4x squared. Reduce by 1, y is gone again. So we just have 4x squared, right? We had 0 first for this first term. With respect to y, this was 0, right? Plus, then we have this, which is 4, okay? 4xz squared, right? You can see that that 0 there is, that 0 there is not really useful. Then finally, we're going to differentiate this same function with respect to z. We're going to differentiate it partially, but with respect to z this time around. So we're going to have differentiate this with respect to z. You know it's going to be 2x squared, right? My rough is filled up. I can't explain, but you know it's going to be 2x squared, right? Then you differentiate this as well with respect to z. Z has a power of 2 there. You multiply 2 with its coefficient, it becomes 8xy, right? You multiply 2 with this, it becomes 8xy. That's the coefficient of z now. You reduce the power of z by 1, it's going to just be 1, okay? Alright, so this is the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z of this same function. Alright, so you can go ahead and add up terms that can be added. Okay, if there is any, just add them up and you get a final form of your answer. Alright, so I'll see you guys in the next video where I'll be looking at maybe application of this. You understand? Core of vector, what do we call it? I'll see you guys in the next video. Bye.